These creatures don't live in forests. They don't fly, nor do they live in water. In fact, they don't live in any of Earth's known habitats. They live on geometric graphs. Confined to nodes and edges, they hunt, flee, and survive. Today, we take an exclusive peek into the secret life of graph creatures.
This video continues to explore the broader idea we've historically called Corgan, short for competitive organisms on networks. It's an environment where AI agents are constrained to graphs. This is in contrast to most other AI environments, where agents live in fully open spaces. This episode investigates predator-prey scenarios on a graph, for now with a single predator and prey. Our environment is set up in the 3D procedural software called Houdini, made by SideFX. The playing field is a graph. Scattered randomly on it are wall obstacles, which block visibility. The two agents are the prey, in yellow, and the predator, or chaser, in red. The agents move along the graph's edges. These short lines show the orientation of the agents, or which way they're looking. The prey wins by collecting all food items, in green. The chaser wins by catching the prey. These diamond shapes are nodes, which act as protective dens. They are a temporary refuge for the prey, which the chaser can't enter. The prey can stay inside only for a limited time, then it must leave. This gray line of sight links the chaser and the prey when they can see each other, if looking in the right direction. The green sight lines appear when the prey can see food if the prey is looking in the right direction. At the geometric level, the agents are points moving along the edges of the graph. The progress of the game is monitored via a state machine encoded in the attributes of both the agents and the graph. On each frame, each agent receives observations and analyzes the situation in its own VEX code. For rule-based agents, their behavior is guided by a set of programmed rules designed to help the agent win. When the agent reaches a graph node, its VEX code decides which edge on the graph to move on to next. The code evaluates distance to food, danger from the chaser, escape routes, etc. If it's in a den, the prey evaluates when to flee and in which direction. The rule-based chaser evaluates visibility and interception paths. All these factors contribute their score to the final decision. The agents can also make U-turns within one edge for split-second decisions. In Houdini, the pipeline is carefully arranged to ensure both agents get access to new info at the same time. The game manager, via its own VEX code, analyzes the game as a whole to detect win or loss conditions, etc. At the end of the frame, the state machine advances by one step. While writing the strategies for the rule-based agents, we had a few interesting findings. For the prey, the strategy of collecting food pieces changes if only one food piece is left, and both the prey and the chaser are nearby. In this case, the prey should not try to prioritize evading the chaser at the cost of not getting the food, as usual. Instead, it should just race to get the food since it wins the game. A few times, we also got false catches, where agents were close in space but on different graph edges, and the game manager declared false victory. We had to fix this. On a graph, for a valid catch, the agents have to be both close and on the same edge. All aspects of the scenario, the number of food pieces, the graph's shape, the time allowed in a den, etc., affect the chances of success for either agent, which aren't necessarily equal. A simple way to gauge these chances is to run a few dozen games and find out the win-loss rate. It turned out that, given our settings, the prey had an advantage. To equalize the rates, we increased the speed of the chaser by a few percent from the initially equal speeds. This equalized win-loss rates and established a performance baseline. Next, we proceeded to train AI agents able to compete in this scenario. This was done with the ML Agents module in Unity. First, we created a few dozen graphs to be used randomly for each training session to avoid curve-fitting ML agents to a specific graph. We quickly found out that learning was very slow, especially for the chaser. We decided to train the agents in a curriculum, that is, in progressively harder stages. The difficulty was controlled with graph size, number of food pieces, and a less capable opponent. This graduated training made learning possible. We found out that the prey learned far quicker than the chaser. The prey acquired basic competency within under 1 million steps, though the whole training took 20 million steps. On the other hand, the chaser needed about 5 million steps for basic competency, while the whole training took about 40 million steps. Another finding was that the graph size affected the chances, with smaller graphs seemingly favoring the prey. For this reason, chasers started training on large graphs, while the prey could use smaller graphs initially. Once the agents reached a learning plateau in Unity, we moved back to Houdini. Our goal was to pit rule-based and AI agents against each other, so the next step was to incorporate the ML agents in Houdini. In practical terms, this requires Houdini to use Unity's training weights, that is, the ONNX file. This is done with 3 nodes. The first one translates the game state into numerical observations accessible to the ONNX. The second node performs the inference, and the third one translates the output into Houdini action. In case you're interested, here's how the weights in the ONNX look. This initial gem seemingly interprets observations. The second, bigger gem is presumably the decision maker. Good luck figuring out what any of these values mean. With this Houdini setup in place, each agent's brain, so to speak, could now be selected with a switch. With the agents developed, we can now watch them play in a few sample games, using different combinations of opponents. First, a case when both the chaser and prey are rule-based. We'll use icons to symbolize the brain type. Squiggly brackets and a colon stand for hand-coded or rule-based. Here we go. Now a rule-based chaser versus ML prey. Here's an ML chaser versus rule-based prey. Finally, both agents are ML trained. Here are our findings based on matchups between different agent types. As already mentioned, for rule-based agents to equalize win-loss rates, we made a quick fix. The chaser was simply made a bit faster, but this had unintended consequences in ML training. The ML chaser's performance was amplified as the chaser exploited its advantage to the max. On the other hand, the ML prey could not compensate. This produced a beast of an ML chaser, which dominated in all matchups. In hindsight, a better way to equalize chances would have been to tweak the environment. More food to collect, less allowable den time for the prey, etc. We found out that the agents learned better in a curriculum, that is, training done in stages. The different roles, chaser and prey, trained better in their own training regimens. An ML agent can outperform its rule-based equivalent. The learning process can be skewed if an agent has some built-in advantage. If this video is well received, future episodes may follow, with more agents, more complex graphs, changing topology, etc. This way, more secrets of graph creatures will be revealed.